Well, good evening. It's 5:34 on Monday, the 17th of July, 2017. Supposed to be Physics 201, Physics 1, trig-based physics. And right now I'm the only one, 202. And right now I'm the only one in the room. So I hope some of the students are coming. I know one student was here for the 201 class and we lost power. We just had, we were finishing lab at the time, so we did get to finish lab, and several of them turned it in, but then I don't know if she's coming back or not, but she seemed to have left because power stayed off for quite a while. But it did come back on about a half hour ago, and bright and sunshiny outside, perfect weather, no wind, anything, so we do have power back, so I can go on and conduct class. Let me give you a couple of announcements. Tomorrow morning I have a doctor's appointment at 8:20, but I have to be there at the clinic for labs by 7:20, so I won't be on campus at 7:45, which is usually my start time here, because I'll be at the clinic either doing labs or the appointment. Since the appointment starts at 8:20, I hope that we'll be through by 8:40, but it's not likely. But we could be, let's just say 8:45 at the earliest, probably would be reasonable. And then if I can come back from then, I should be back on campus by 9:30. But I've already made up the class that I will be missing tomorrow. Last week we did an extra 55 minutes both Tuesday and Thursday to make up for the hour and 50-minute class we were going to be missing tomorrow. So whenever I get back to campus, it could be anywhere as early as 9:30, more likely closer to 10 o'clock, and possibly even later than 10. So if I'm not in my office at 10 o'clock, I will be there soon. But normally my office hours start at 10. But I'll start them as soon as I get on campus, whenever that is, either before 10 or after 10. Then my afternoon class should be no problem. And everything else should be good for the rest of this week. Next week, however, I do have, I'm pretty sure, I've got to check the date on it, but I believe Tuesday morning at 10, we have what they call a planning meeting. And so we're required to be there. I've still got some work to do for it, so I'm going to be doing that tomorrow and Thursday, and probably over the weekend too. So anyway, I've got that to take care of then, and so I will not, if the meeting is Tuesday morning at 10, not tomorrow, but the next Tuesday, then my office hours from 10 to 12 will probably pretty much be shot. The meeting is going to go at least an hour, and then I need to be in the room for the beginning of the next meeting, because we share some of the same unit goals with the next group, so I'll be there for that. But then I hope to be able to leave by 11:30 to be back on this campus by 12 o'clock, because I have a 12 o'clock class here and I don't want to miss it. So anyway, I hope that will be the last adjustment to office hours. Let me say this, this class, 1 out of the, 8 students, 1 out of 8 has turned in a paper, a research paper. That's pretty low, I think my lowest percentage. So please, folks, you only have 1 and maybe 2 weekends left. I can't remember when the last day of class is and the first day of finals, but please get the paper in to me sooner rather than later. It'd be great to have them all in by next Monday. Sooner if possible, but by next Monday, and definitely by Wednesday. Okay? The last person did finally turn in her test for test 1 through 4. So I had returned some of those to you when I thought she was not going to be continuing in the class because she hadn't paid. But then she paid, so I can return those tests 1 through 4 to you if I haven't already. However, she hasn't turned any of the labs, so I can't return those that I haven't returned to you already back until I get those from her or find out that she's not going to do it. Okay. That's about all I can think of now. So let's get on to where we left off last time, which was in topic 23. Topic 23 is mirrors and lenses. We're in 23.2, which is images formed by spherical mirrors. And we had started this process last time, and we're now looking at, we're at the top of page 756. Making an array diagram requires knowing the position of the object, location of the center of curvature. To locate the image, 3 rays are constructed rather than only 2 that we've been constructing, and we will delve into that now. So let's take a look at this, and I'll give you the features that are important. Okay, number 1, locate the, let me get my pen in the right color. Okay. Locate the object, okay? Usually the object will be given some distance away from the mirror, and that would be the center of the mirror, along the principal axis, okay? So you locate the object there, give it an approximate height, okay? Now, the 3 rays that we use, oh yeah, let me locate the other thing. When we're given the mirror, usually we're given its radius of curvature. That's how far in front of the mirror, if it's a concave mirror like this, the center is. That's the radius of curvature. We know automatically the focal point for that mirror is going to be halfway between the center and the mirror itself on the principal axis. Okay? So we can locate the focal point there. Then we hit our 3 rays. The first ray that they show here is the one parallel to the principal axis. All rays coming in parallel to the principal axis must go through the focal point of a concave mirror. They will go through the focal point. So draw that one. The second one, every ray that goes through the focal point bounces right back to the focal point. Okay? No, I'm sorry. Wrong. Every ray that goes through the focal point bounces back parallel to the principal axis. So if they go in parallel, they go through the focal point. If they go in through the focal point, they bounce back parallel. So those 2 are sort of inverses of each other. Those 2 give you basically a great idea where the image is. Okay? Then the 3rd ray we draw through the center of the mirror. If you go through the center of the mirror, you're going along a radius, actually along a diameter as well, but radius, and anything that hits on the radius, along a radius, bounces back right through the center. So that's your 3rd point, and when that gets on top of the point where the other 2 are, you feel very good about that being your image. Okay? Now, things to note about the image. First, if the object is outside the center of curvature of the mirror, okay, then the image that's formed is 3 things. It's real, because there actually is a point on the front side of the mirror where the rays actually converge. So that makes it a real image. Secondly, it's inverted. And frankly, every real image is an inverted image. Remember that. You can't have them. So when it asks for whether they're inverted or not, if it's real, it's going to be inverted. Now, the other thing is the image is reduced compared to the object. It's smaller than the object. Inverted, sure, okay? It's smaller than the object, okay? Those are what the ray diagram tells us, and that's when the distance from the object from the mirror, is greater than the radius of the mirror, okay? Now, the second type that we're going to do, and I don't know why they don't go on and give you the equations now too. We've already done the equations. I wish they would do those at the same time. But let me remind you what the equation is for the concave mirror. Okay? Basically, that equation is 1 over distance of the object plus 1 over distance of the image is equal to 2 over the radius. Okay? You could think of that as 1 over the focal length. because the focal length is 1, no, I'm sorry, that's not right, 2 over the radius, okay? Let's take a, well, no, we don't have any numbers here, that's why they don't use the formulas. The magnification, let's go on and hit that as well. And we had that earlier. The magnification is equal to either the height of the image over the height of the object. That's how we usually think of it. In this case, that would be a negative number smaller than, or between 0 and -1. Negative because it's inverted, between 0 and -1 because the image is smaller than the object. Okay? The other way you could do this is minus distance of the image over distance of the object. Okay? Again, the minus, I'm sorry, this one has the minus sign there because with this one, both the distance from the image is in front of the mirror, so it's a positive distance. The distance of the object is in front of the mirror, it's a positive distance, but the distance, so you see the magnification again comes out negative and between 0 and -1. Okay? So we don't have any numbers to put with them, but those are the two things you can find out right now. Okay. Let's move to the B figure in figure 2313, and that's this one. This time we have a concave mirror, but we place the object inside the focal point, okay? Inside the focal point. So the object is between the mirror and the focal point, and let's draw the object here. Now, generally do a small object here because you've got to deal with a lot of lines here. So our first ray again is the one that goes parallel to the principal axis, hits the mirror, and has to come off through the focal point. There it goes. Okay. The second is the image, that is the ray that comes as if it's coming through the focal point. Of course, and it would be the ray coming off here, but it doesn't leave the object until it's inside the focal point. So you just dot the lines from the focal point there, continue up here, and if it passes through the focal point, or looks like it would have, then it comes off parallel, which it does. And then the third one is the ray that comes through the center, bounces off, and goes right back through the center, because angle of incidence equals angle of reflection along the radius. And there, sure enough, is the object. I mean, there was the object. But if you look at this, these three rays, the exiting rays, the reflected rays, are diverging. They're not converging. They can't converge. So what you do is dot them backwards. The first one dots back to there. The second one dots back to there. The third one dots back to there. So it appears to be an image behind the mirror. Okay? It's not really an image back there. It's a virtual image. So the object, when it's between the mirror and the focal point of a concave mirror, the image is virtual because it's where the rays appear to have converged was behind the mirror. Of course, they can never be behind the mirror. It doesn't allow rays back there. And because it's virtual, it is upright, and it is, in this case, concave mirror, object inside the focal point, always larger than the object. Okay, upright because it's virtual, and larger. Okay, and let's take a look at our equation. 1 over distance of object plus 1 over distance of image is equal to 2 over the radius. Okay, now in this case the object is in front of the mirror, so that's a positive quantity. Fantastic. I'm so glad to have a student. I get so bored already, but bored talking to myself, so I'm glad you're here. In case you're wondering why no one else is here, I'll give you a hint. The school lost power back when the big thunderstorm came through, and it really wasn't as bad a storm as we've had many, in fact, most days. but evidently it knocked something out. They said traffic lights were out, things. We were without power for probably more than an hour, maybe considerably more than an hour. I was fortunate, my last class, the Physics 1 class, was doing the lab at the time, and we got most of the lab done. I only had a few things to do. We were down in a lab room that was well lighted, so with outside windows. So we were able to finish the lab, and then the students either stayed down there or came up here where it was a little brighter, and did the written part of the lab, and most of them turned it in. A few left fairly early because they thought the power was going to be out, and it did stay out for the rest of the time. However, I did get to eat my lunch, for the first day probably since the beginning of the term. Okay, I usually get a little bit of it eaten, but not all of it until right at the end of the day. But I got everything eaten. I sat in here by the window. I got that done, and then about the time I was ready to start grading papers and stuff, then the power came back on. It was about a half hour or so ago. So glad you're here. But some of the other students, one student is in both classes, and she was assuming that I think that the power wasn't going to come back on, but it has. So if you are on a list with them, let them know we are having class.
Are we doing lab today?
Let me see. I can't remember how long this chapter is. I'm guessing maybe not, because we've got, I kind of don't think we're going to have time to finish this today. Well, I think we have time to finish the chapter today, but we won't have 2 hours for the lab. Ah, here she's back. Good. And Power's back too. Okay. So I doubt if we'll have lab in here today, but we will finish the chapter, I think, and start on the next chapter. And then we definitely have the lab. Now remember, the last chapter and this chapter, the labs are together. There's very little way to separate reflection, refraction, and what we're doing now. Look at this, they keep coming in. That's great. Okay. All right. Now from 0 students to 3 students, probably within 5-10 minutes. Okay. So what was I saying? I don't think we'll have time to do the lab today. We'll finish the chapter, I think, today, but not the lab. So we'll probably go on and get started moving on the next chapter. And by the way, the next chapter is we're not going to do wave optics, and optical instruments. Those are great chapters, but we'll probably go on to topic 26, which is relativity. And we may get started on that tonight. Depends on how far we get on the other one. Now, topic 26, relativity, I'm not certain. I cannot imagine what lab we can do on that. If I find a good lab, we'll do it, but it'll probably be a paper lab. So stand by for that. It's going to be really tough to do a physical lab because I don't have equipment to do relativity. I can't think of anyone who does. Yes? I'm sorry? Oh, she won't? Okay. I knew she wasn't here this morning for the math class, so I figured she might be on. Okay, but thanks for telling me. Okay. I got started on page 756, still on 756, but on the second figure of that. It's funny, the figures in the text and the figures on the slide are a little bit different. I find is so-so. There is a sense, I kind of like the old ones better. This is a bottle of colored liquid. It's easy to see. but the other one's a candle, and that's pretty easy to see too. I think a little easier. Okay, but since y'all are here, let me turn on the projector. Put the lights over. And it turned out being a very pretty day today. It was so stormy during my last class, actually during the last lab, and that's what knocked the power off. Any questions before we get picked back up again? I'm waiting for the projector to come on. Any questions?
Our final is 2 weeks.
Okay. I'm trying to recall, we have class this week and next week. Okay? And I can't remember if we have class that first Monday of the following week and then finals, or if finals start Monday of that following week. Does anyone recall? I looked it up once, but I don't remember what the result was. It seems like this term started on a Wednesday, not a Monday. I'm pretty sure of it. Huh? So I think we end on a Wednesday, on a Monday, and the exams start on Tuesday or Wednesday. I don't know that for sure though. Seems like it ought to be that way, but it may not be. Yeah, you can look it up on Blackboard, on the website, the academic calendars there. There's several places you can look. Yeah, it's on my syllabus. I looked it up for the syllabus. I just don't remember what it was. Okay. When I started this evening, any other questions? By the way, and I said this earlier, in this class, only one student has submitted a paper. That means all the rest of you still have papers to go, and here is FA. I'm beginning wondering if you were in town. Okay. All right. So we've got half the class here now. Oh, and by the way, let me go on and say this while I'm thinking of it. That last student who I thought was not going to be in the class because she hadn't paid and she had some health issues, she finally did pay and submitted a bunch of work. So right now I have the first 4 tests. I think I've already returned most of those to you, but I think I stopped when I realized she might be coming back. So she hasn't turned in any labs yet, so I can't turn back your labs to you. But I will take a look at the test. And I believe, yeah, hers is the first test. I returned all of yours to you. Okay. Then, second test. I returned some of them to you. Let me make sure on this. Yeah, everybody's turned in the second test. So, this is such a big pile of papers. Okay. Charity's not here to get hers back, but Courtney is. Okay. All right. Yes. I'm sorry?
Have the lab from 201 today.
Okay. How about at a point or something? If I have to dig through it and find it. I'm in the other stack now. This stack. Okay. Here is test 3. I don't think I returned any of these to you. He is not going to be here. Megan is. Yes. Charity is not. Is. And the bottom part of the alphabet. Okay. And I can't return any labs until I found out that she's going to turn them in she's having difficulty doing them, but I said listen to the YouTube and answer the questions that you can. All right, FA is here. This is test 3. Actually test 4. Here is not. Negative is. And that is. Charity, of course, is not. And first is. Yeah. That's as far as I can go because that's also turned in. So, if anyone else comes in, I'll have to just get them for them at break time or at end of class or whatever. Okay. Any other questions? Any of you find when the last day of class was? I didn't know if you all were looking. Oh, that's all right. I thought you were looking.
8th.
Huh?
It's August 8th.
No, that's the last day of finals.
Okay, well, August 3rd.
August
I
what?
think last year was July 31st.
What's that?
July 31st.
July 31st is the last day of class. Is that right? And let's see, today is the 17th, so that means we have class this week, next week, and the Monday of that last week. So you have 2 weekends. Okay, I'd say get on the paper sooner than that. Okay, it looks like with that then, I think there's a good chance we will finish this chapter. I think we'll finish relativity and have at least a paper lab on that one. And then we'll go back and pick up one of those chapters we skipped that looked like it was going to be a really good chapter. I think it was 20.
So on that Wednesday, will that be your final term?
What, the
Or last
second,
class is that Monday?
last day of class is Monday the
So-
31st, right?
Will we get the final that day?
I'll give you the final on the 31st and you can turn it
So can
in.
we do what we did last summer, just stay after and finish it?
If you want to, you certainly can. Just like every test, you could do that now too if you want
Yeah,
to. Also,
okay.
Yeah. And I'll also be returning all your papers to you, labs and tests or whatever, whether anyone's turned them in or not. I'll get them everything back to you. I'd like for them all to be in before then so I can get everything back to you well before that. But if not, then that last day of class I will return all papers to you. Okay, and that means I can't accept any after that day. Okay. Now, of course, your research paper, I can't return those to you because periodically they ask for samples of student writing, so I have to hang on to them. So. Okay. Any other questions? Okay. Where I was, I had done, before anyone got here, on page 756, the figure there, figure 2313, I had done the A one and it started on the B one. Okay? In fact, I had done everything on B, but then I was putting the formula down here so you can see how these work too. Okay. Now, the book likes to use P and Q for distance of object and distance of image. And that's fine, it's perfectly fine, but to me, it so much makes more sense to say distance of object and distance of image, DO and DI. Also, I like to do height of object and height of image. They do H and H prime. So you have to remember which is the prime and which isn't. If you put the subscript, it's pretty obvious what it is. Okay? So this is, and I'd already discussed it, the object inside the focal length, between the mirror and the focal length, that will always, for a concave mirror, always be a virtual image, upright image, magnified image. Okay, the image is larger than the object. And I went through the diagram so you can see why. Now let's look at the equation and see if that makes sense too. Okay, distance of the object is positive. By the way, distance of the object is always going to be positive. You can't put an object on the back side of a mirror. It's got to be on the front side of the mirror. So distance of the object is positive, but a small number. Distance of the image The image is back there. It's a virtual image. It's not really back there, but that's where the image appears to be. So that's a negative quantity. It's on the back side of the mirror. So this will be 1 over di will be a negative, minus 1 over that distance from the mirror. And then 2 over r is 2 divided by the radius, which is the distance from the center to the mirror itself on the axis of the mirror. Okay? So then you'll have a 1 over dO minus 1 over di is equal to 2 over r. R is always positive. The radius of the mirror is always positive. The other equation that's important is the magnification equation, and that goes like this. Capital M is equal to, and there's actually 2 of them. The first is height of image over height of the object. Okay, that's what we call magnification. And in this case, the height of the image is larger than the height of the object, so therefore we say this is magnified. The image is upright, so it's positive, so everything is hunky-dory there. By the way, a negative magnification means it's inverted, but the absolute value of magnification, whether it's reduced or magnified. The other definition of this would be minus the distance of the image over the distance of the object. That is the other thing. And if you'll notice here, the distance of the image from the mirror to the image is larger than the distance from the object to the mirror. But it's behind the mirror, so that's a negative quantity. So you have a minus negatives, which makes it positive, and di is greater than do, so that means it's magnified. So both of these give you positive large numbers larger than 1. Okay? And that's what you got. Now, does anyone want to tell me what kind of mirror this is? I bet you all 3 of you have one. All 4 of them. Second? Don't y'all have a makeup mirror that blows up, that makes your image bigger?
Magnifying mirror.
Magnifying mirror. I know my wife has several. One hangs right next to the plain mirror in the bathroom, and boy, it makes things big. Okay? You call it magnifying mirror?
Yeah.
Okay. I've heard her call it makeup mirror. Now, yeah, the one in your compact probably is just a plain mirror, isn't it? Does it blow you up, or does it? Okay, yeah. But this one does. Just like this is the actual candle in front of the mirror. That's the one. The image of the candle behind the mirror. Okay. Upright, virtual, larger than the object. The third one here in this figure is this one, a convex mirror. Okay. Sometimes also called a diverging mirror, because you can't put this object anywhere that's not going to have a virtual image behind the mirror, upright and reduced. No matter where you put it, that's going to be the case. Well, here's your object here. The object is always in front of the mirror, so the DO is always positive. Okay? And our 3 rays that we use to determine where the image is, the first one is the one that goes parallel to the angle, the axis of the mirror. Oh, Samuel decided to grace us with his presence tonight. Aren't we lucky? Okay, good deal. Glad that you're here. And by the way, before you go, I've got the first 4 tests I can return to you, because the student who paid late, added late, and that kind of stuff, I thought she wasn't going to pay because she was having health issues. I had basically wiped her name off, and then she did pay and finally started turning in stuff last week. So I got it on Thursday and got it graded, so I can return it. I think I've already returned your first test, which I didn't know she was coming back at the time. In fact, I didn't even know she was going to be in the class at the time, but she hadn't paid, so I didn't worry about it. But then when I found out she might be coming back, I didn't return any more to you, so I can return the first 4, because everybody's turned those in. so far she hasn't turned any labs, so I can't return any more labs that I've already turned back to you. But once I get those, if she turns any in, then I'll be able to turn some of the labs back to you as well. Okay. And FA, by the way, oh, you wanted something from the first class, right?
Yeah, the last one.
Okay, so remind me when we take a break or at the end of the class. All right, so here's your object in front of the convex mirror. I did mark, yeah. In front of the convex mirror, and by the way, the object distance of the object is always positive. It's always in front of the mirror. The first ray is the one parallel to the axis of the mirror. Here's the axis of the mirror down here. So the one parallel to that always leaves as if it came from the focal point. Now the focal point of a convex mirror is behind the mirror. It's got to be, because the center of the mirror is back there. Okay? So that means the focal point, the focal length is negative, and this is the old boy. I think last time I said radius is always positive. I think in this case the radius is negative too, because it's behind the mirror. Okay? So the ray that comes in parallel here, it acts as its reflection acts as if it's coming from the focus. It can't come from the focus because it can't get to the focus. It's behind the mirror because the center is behind the mirror. But it acts like it came from there, so it goes off in this direction. Okay? The second ray is the one that goes toward the focal point. It can't reach it because the focal point is behind the mirror. So when it hits the mirror, it comes off the mirror parallel to the axis. So the first one goes in parallel to the axis. It comes off as if it came from the focal point. The second one goes toward the focal point, bounces off the mirror parallel to the axis. Those two are kind of inverse of each other. And then the third ray is always the one that goes toward the center. It can't get there because it's behind it, and it comes off in the same direction because that is the normal, the instance ray and the normal ray are both aligned with each other anytime you go through a radius or through the center of the mirror. So those three, here, here, and here, are diverging rays. Can't possibly have a real image. So what we do, we extend each of them back from their rays to where they would be going, toward the focal point for number one, parallel to the axis of the mirror for ray 2, and toward the center of the mirror for ray 3. And sure enough, all three of those meet or convert. They don't really converge. They meet there where the tip of the image would be. Now, one line they have in here that's unnecessary. No, it's completely unnecessary, is this one here. I wish they hadn't shown that line. There's nothing that really goes there. There's no reason for it to be dotted back there. Okay? Oh, I guess it is. It's showing it's going toward the focal point, so maybe I'll leave that alone. Okay. Yeah, it's okay. It's showing where it's going to. It never gets there, of course. Can't go through the mirror. Okay, now what can we say about it? The object, of course, is in front of a convex mirror. Objects are always in front of mirrors, so the distance of objects are always positive. The image, however, is behind the mirror, so therefore it's virtual. And here's the hint. I've said it before, I'll say it again. If it's a virtual image, if the image is behind the mirror, it's a virtual image. And if it's a virtual image, it's always upright. Those two go hand in hand. If it's behind the mirror, it's virtual. If it's virtual, it's upright. Okay? Now, the next thing to note here is that the image is smaller than the object. And in the convex mirror, that's always going to be the case. Now, I bet you've all seen these two. I know you have, whether you realize it or not. Okay? Have you ever been in a grocery store or other store that they had these big mirrors up high somewhere, and that's so the manager up front can look and see down every aisle, and he can see everything going on there. Shoplifting, spillage, things. those are always convex mirrors. The images are always small, virtual, they're upright, but they're always small. That's what this is. The other place where I know, I'm pretty sure that every one of you have seen one, you all drive a vehicle sometime or another, right? And you never do, okay? The right-hand mirror, I bet you has a little printed thing at the bottom. I don't know if you've ever bothered to read it. It said the image is appears further than they are. Huh?
The image is closer than it appears.
It's closer. The object is closer than it appears. That's what it says. The object is closer than it appears, which means the image seems further back. Okay? Because the object is always larger and the image seems smaller and further away. And that's because it's slightly convex. So you can see your blind spot. You get a wide angle. They call this a wide angle lens. Not lens, mirror. So you can see more. That's why the manager at the grocery store can see down every aisle, because there's lots there. Okay, so the image is smaller than the object. Let's see what our equations say. 1 over distance of the object, and again, the book uses P for that. I prefer DO. Plus 1 over DI, distance of the image, the book uses Q for that, is always equal to 2 over R. Okay. Now this one I really need to stop and think a minute. You know the distance of the object is always positive because the object is always in front of the mirror. You can't have an object behind the mirror. It wouldn't be an object, okay? The image, though, is behind the mirror, so this is a negative number. And the radius, this is the thing that I'm a little concerned with. The radius is behind the mirror. So from the center to the mirror, so I think that's a negative radius as well. Okay? I'll have to actually do something to check on that. The other equation, of course, is this one. The magnification equation is always height of the image. The book uses H prime there. I like height of image over height of object. And here, of course, that's a reduced number. The image is smaller than the object, so therefore that's a positive number because they're both upright, but a number between 0 and 1. The other is minus distance of image over distance of object. Okay? Well, distance of image is behind the mirror, so it's negative, but the negative negates that and makes it a positive number, so this is, but the distance of the image is closer to the mirror here than the object is here, so again, it's a positive reduced number. Positive meaning it's upright, meaning it's virtual, and a number between 0 and 1 says the image is smaller. I like to call that reduced. They say smaller, whichever. Okay? Any questions on how we use the ray diagrams? 3 rays always. One parallel to the axis that goes through the focal point or acts like it came from it. One toward the focal point, it comes back parallel, and the other one toward the center comes back in the same direction. Okay? And they should, those 3 either converge on something, or if they diverge, they look like they're converged behind the mirror. All right. So notes on the images. I think I've said these. Let's get them again. With a concave mirror. Concave meaning it's like this, okay, like the mouth of a cave. Concave mirror, the image may be either real or virtual. What determines it? What determines whether that image of a concave mirror is real or virtual? I'm trying to read my script.
What determines it?
What's that?
You said what determines it?
Yeah. If the object is in front of the center of the mirror, in fact, I'll say that in front of the focal point, then it's going to be a real image. And what are all real images? Inverted, exactly. Now, they did go into this, but I'm going to tell you now. If the object is between, of a concave mirror, is between the focal point and the center, then the image is real, but outside the center, magnified, but of course inverted because it's real. If the object is, okay, they just say if the object is outside the focal point, okay, the image is real. That is true. When the object is at the focal point, the image is infinitely far away. Now you probably, if you haven't done this with your magnifying mirrors, try it. It's sort of fun to do, okay? You get up close to the magnifying mirror, and of course the pores look like they're craters on the moon or something like that, right? And then as you back off, that image gets bigger and bigger and bigger, and at some point, have y'all ever seen this? At some point, suddenly you lose the image. Okay? It was upright, virtual, big image. Okay? If you back off at some point, you lose everything. That point is when you're at the focal point. The image doesn't exist, it's infinite. Is no image. Then you back out a little further from that mirror, and suddenly everything is flat. Those are now real images because they're outside the focal point. So the image is real, inverted, and as long as you're between the focal point and the center, it's a big image, inverted, big image. Once you get past the center, at the center, it's inverted, real, but exactly the same size as the object. Exactly the same size as the object. And then when you're outside the center of the mirror, then your image is real, inverted, but reduced, smaller size. So when the object is at the focal point, the image is infinitely far away. When the object is between the mirror and the focal point, the image is virtual. Okay? And those are always magnified for a concave mirror. With a convex mirror, the image is always, always, always virtual. And if it's virtual, it's got to be upright. Okay? As the object distance increases, the virtual image gets smaller and smaller and smaller. So as the object gets further away, the virtual image gets much further away and smaller. Okay? That's for convex mirrors or diverging mirrors. Okay, now we're ready to move on to, there are a bunch of examples there. There's Applying Physics 23.2, Applying Physics 23.3. 23.2 is concave versus convex. 22.3 is reversible waves. Example 23.2 are images formed by a concave mirror. If you want to see any of these, we certainly can do them. Example 23.3 is images formed by a convex mirror, and here we have it. And by the way, I thought I meant to do this and I didn't. I was using the formula in the book. Let's go back to these. Okay? Every one of those, I put 2 over R because that's what the book had. But 2 over R is the same as 1 over F. That's actually the easier way to do it. Well, they give you the radius, so 2 over R will be it, but that's the same as 1 over F. This is the same as 1 over F. And this is the same as 1 over F. And what I was saying before is indeed true. I just checked it to see. When you have a convex mirror, the focal point being behind the mirror is a negative distance. This is a negative distance. Okay? The face in the mirror is 23.4. If you want to see any of these, I'll be glad to do them for you. Okay. Now we get to images formed by refraction. This is 23.3 in the text. It's 23.4 on the slides. Don't worry about that. I just put 2 things in one. So images formed by refraction. Okay? Now they start with point sources, and it's okay. For the life of me, I can't figure out why they do this, and then they get to real objects, but you know, this is fine. Rays originate from an object point O. Okay, this really isn't very useful here, but it is. They pass through the image point I. Okay? Now this is what they call a converging lens. Now, the ends here, remember, are what? What do we call these N1 and N2? N sounds like the first syllable. N, a two-syllable word. We're talking about refraction. The index of refraction.
Index.
Index. Oh, you got it. Good. I'm proud of it. Okay. So this is when the index of N2 on that side of the lens has a higher index of refraction than N1, the medium on the outside. And here is, by the way, your formula. N1 over what I call DO, distance of the object, plus N2 over the distance of the image, I call it DI, they call it Q, is equal to the difference in those, N2 and N1, when N2 is greater, over R, where R is the radius of curvature for that lens. Okay? Now the magnification here, and this is a point source, so that's why this really isn't making a lot of sense here, that the magnification is height of the image, which you don't have a height, over height of the object you don't have a height, and this will be minus N1 DO, DI, and I call this HI, height of image, height of object, minus N1 DI over N2 DO. That's how I like to tell it. The real images are formed on the side of the opposite from the object. Real images are formed over on the other side. Not like a mirror where it's reflected. This is refraction. This is bending the rays. Notice here the rays bend. Here's your normal line. Okay? Something like this. Okay? There's your radius. So the normal line comes right like that. And the angle of incidence and angle of refraction are related to the indices. You can go back and check those out. That was the last chapter we did that. So the rays making small angles with the principal axis diverge at a point object at O and pass through the image point I. Again, I don't find the point sources and point images to be telling you a lot. But again, they use P and Q. I like to use distance of object, distance of image. Right. With a lens, the rays bend into the medium, so therefore the distance of the image, Q, if it's on the opposite side of the lens, that's where it's supposed to be. So that's what's positive. So I like to call this DO and this DI, and this is always positive, and when the image is on the opposite side of the object, then that is positive as well. Okay? And everything works out fine. All right. So here's the sign convention for refracting surfaces, different from what we use for reflecting surfaces. Okay? Object location is always, the symbol is P. I like to use DO. It's object location, distance of the object. It's in front of the lens. Now, if the object was behind the lens, you don't usually put objects back there. You put objects in front of the lens. So this doesn't really make sense. With a lens, you could have it back there, but it doesn't make sense. Okay? The image location, if it's in front of the lens, then it's negative. If it's behind the lens, it's positive. So if it's on the same side as the object, it's a negative image location. If it's on the opposite side of the lens, that's where it's supposed to be. So that's a positive location. The radius Oh boy. Yeah. There are actually two radii. Okay? We're going to only use what they call the principal radius. Okay? And that principal radius, if it's in front of the lens, in other words, if your lens is thicker at the edges, thinner in the middle, thicker at the edges, that's called a diverging lens. So there your radius is in front of the lens. That's a negative radius. If it's behind the lens, then you have a converging lens, and that's the place where it should be, so that's positive back there. The image height, if it's an upright image, it's always positive. That's what it means. I can tell you right now that's going to be what kind of image. If it's upright, it is. The image is upright. The image is. The image is upright. The image is. Okay. Okay. It is positive. The sign for it is positive. But what is the nature of that image? As in real or virtual? Virtual. Upright is always, 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 always virtual. If it's an inverted image, guess what? Guess what? It's real. Always real. Okay? But if it is inverted, then the image height is negative. Positive if it's upright, negative if it's inverted. But if it's upright, that means it's a virtual image. If it's inverted, that means it's a real image. Okay. Now, let's look at what they call a flat refracting surface. Okay? This is the light coming through the windows. Okay? The image formed by a flat refracting surface is on the same side as the surface of the surface as the object. That means it is virtual. If it's on the same side as the object of a lens, now not of a mirror, of a lens, then it's got to be virtual. Okay? The image forms between the object and the surface. The rays bend away from the normal surface since the N1 here is greater than N2. In this case, if the object is embedded in the lens, okay, and it's a flat lens, then the rays, here is the normal line, okay, the rays for the smaller index of refraction, that angle is greater from the normal than it is. It bends away from the normal, okay? So that's a diverging situation. These rays are going like that, getting further apart, so the image has to be where they look like they're coming from. That's inside the lens. So, when the image formed by a flat refracting surface is on the same side of the surface of the object, the image is virtual, the image forms between the object and the surface, the rays bend away from the normal since the normal N1 is greater than N2. Okay? Now, where have you seen that? Okay? Have you ever been standing in a pool of water, or possibly a bathtub? If you do that, look down at your feet look like they're closer to you than they are. Your legs look shorter, in other words, because the image is here when the object is really there. That's an extreme example, but yeah, your foot is in the medium with the higher index of refraction. So your foot, or the ruler, or anything else looks like that. Okay. How about the atmosphere? The atmosphere does refract. Many interesting results of refraction of the atmosphere. This is 23.4 in the text. Now, in the text, the flat refracting surface that we had on the last slide is 23.3.1. Oh, here's some quick quizzes. I almost skipped them. Didn't mean to. And by the way, underwater vision, that's applying physics 23.4. So if you want to talk about that, we can. Here's the quick quiz. A person spearfishing from a boat sees a fish located 3 meters from the boat at an apparent depth of 1 meter. To spear the fish, should the person aim at the fish, above the fish, or below the image of the fish? It says at the image of the fish, above the image of the fish, or below the image of the fish. Fish is located 3 meters from a boat at an apparent depth of 1 meter. Which way should you spear? Let's go back here. Okay? Here's what the deal is, folks. You're out here in the air, the fish is in the water. N1 is greater than N2, right? The fish appears to be here, 3 meters from the boat. Do you do at the image, below the image, above the image? You're down here, you aim toward the object. You can't see the object, you see the image, you aim below it. And be sure you allow more than 1 meter of spear, because it's going to be deeper. Okay? So that should be below, if I'm interpreting what they're meaning by below correctly. So this is 23.2. 23.2 is C, which is below the image of the fish. Good deal. 23.3. True or false? The image of an object placed in front of a concave mirror is always upright. The image of an object placed in front of a concave mirror is always upright. True or false? Absolutely. Because if you're inside the focal length, it's upright. If you're outside the focal length, it's inverted. And if you're at the focal length, you get no image at all. Okay? B. The height of the image of an object placed in front of a concave mirror must be smaller than or equal to the height of the object. True or false? The height of the image of an object placed in front of a concave mirror must be smaller than or equal to the height of the object. Say again? False, exactly, because that magnifying mirror is a concave mirror. And there the image is certainly bigger, okay? So we got a false, false, okay? How about number C? The image of an object placed in front of a convex mirror is always upright and smaller than the object. True, because that's always going to be the case. So we got a false, false, true. What do they have? False, false, true. Good for them. They got it right. Okay? Example 23.5 is gaze into a crystal ball. If you want to see that, we can talk about that one. 23.6 is the one that got away. This is spearfishing again, and you obviously didn't adjust like you were supposed to. So now we're ready for atmospheric refraction. Okay? As we said, there are many interesting results of refraction in the atmosphere. First, the sun's position, especially on sunrise and sunset, it's pretty far off from where it really is. It appears to be different. Okay? And another really interesting feature is what we call mirages. Have you ever seen one? I'm sure you probably have and didn't realize it was a mirage. Have you ever looked out at the black top of a road, but then you think it looks like water standing on it, but you know it's not? It seems to be reflecting. You're not, okay? Pay attention sometime. I bet you'll see that and say, oh, that's what he's talking about. Okay, let's take a look at this. The light rays from the sun are bent as they pass into the atmosphere, of course. Now, why they have you up on the North Pole, I'm not sure. Okay, I guess it bends more there, I guess is why. Not only on the pole up, but close to it, like inside the Arctic Circle. If the sun is really here, and the rays go straight from the sun through space, but once they start hitting our atmosphere, they start bending. Because the atmosphere, space has an index of refraction exactly 1, and the atmosphere has a little bit greater than 1. So they're going to bend toward the Earth. So it looks like the sun is over here, but it really is down here. Okay? Light rays from the sun are bent as they pass through the atmosphere. It is a gradual bend because the light passes through layers of the atmosphere. The very uppermost layers are very thin. They don't bend much, but each layer has a slightly different index of refraction. Okay? The sun is seen to be above the horizon even after it has fallen below it. And on the other hand, it seemed to be above the horizon even before it gets above the horizon. So even on equinox, when you're supposed to have equal day, equal night, it'll look like the sun's up a little bit before when it really is, and it sets a little bit after when it really did set. Actually, it is equal day, equal night, but it appears to be a little bit longer daylight. Okay. So that's the atmospheric refraction and the sun's position. Here's atmospheric refraction and mirages. Okay? A mirage can be observed when the air above the ground is warmer than the air at higher elevation. Now, that's why I said looking on a blacktop. Okay? Because typically there, that air right above the blacktop road, the paved road, is considerably warmer than the air just above it. Okay? That happens quite often in the desert. Okay? The air right over the sand here, because so much light is reflected directly off the white sands, then the temperature here is warmer than it is a little bit higher. Okay? And because of that, it has a higher index of refraction. Okay. The air is warmer, so it has a lower index of refraction. The rays of path B, because you see this ray coming down here is bent upward because the density of the air here is less because it's a higher temperature, so it bends this ray like this. So you're looking here and seeing the cactus here, okay, but it looks like you're also seeing a reflection of the cactus down there. Now, cacti are not particularly interesting, but if you're in the desert and nothing was there, and all you see up here is blue sky, and what you see down here looks like blue, which you assume to be water. And this is what would drive those settlers crazy. They look out over the desert, they're parched thirst, look out over the desert, and the sun, hottest part of the day, the air just above the desert floor would be very hot, and it would be reflecting the blue sky off the desert. And they say, look at that, water, let's head toward it. And they head toward it and never reach it because it's not there. That was just a mirage. The rays of path B are bent by refraction. The observer sees both the upright and the averted image of the cactus. Or if the cactus is there, you see the image of the blue sky down here, and you think it's water. And look at that sometime on a blacktop. Now, here's what you need to be doing. You need to be looking in the same direction of the sun. So if it's a east-west road, that's going to do best early in the morning or late in the evening. Looking at that east-west, the sun is going to be directly in line with you, and you will see that mirage. And there is a picture in your text. If you have the text Notice the reflection of the cars in the photograph is a mirage. That is not water on the road. That is the road being so much hotter than the air above it. Because look at that clear sky. There hasn't been any rainfall there. And you are actually seeing an image. I have never seen one that clear. I think this must be a very, actually it says it's New York City, but I don't think that's where the picture was taken. I don't know. Pretty remarkable there, but that's the mirage. Okay, now let's look at thin lenses. Okay, this is section 23.5 in your text, 23.6 on the slides. A thin lens consists of a piece of glass or plastic ground though that each of its two refracting surfaces is a segment of either a sphere or a plane. Okay? That's a strange way to say it, but it is. The lenses are commonly used to form images by refraction in optical instruments. 4 of you are wearing thin lenses, right? Your glasses are thin lenses, okay? I have a thin lens in my right eye. I had a cataract removed and they replaced it with a lens. An artificial lens, not a human lens, but an artificial one, okay? In my left eye, and I'm sure for y'all, both eyes, you have sort of flexible lenses because you have muscles that compress and contract it, so you change the focus of that. My left one doesn't do a good job of it, my right one doesn't do any at all because it's not flexible. So, lenses are commonly used, okay, I think we already said that. So here are some illustrations of thin lenses. Okay? This is a convex surface. That's a convex surface. Since they both are convex, we call it a biconvex. Thinner at the top, thicker in the middle. Biconvex. Okay? Now this is a convex concave. This side is convex, that side is concave from that side. Now this is also a converging lens because it's thinner on the top, the edges, thicker in the middle. This will still converge. Okay? You could have had convex concave if this one was just slightly convex here and this was more concave here, then they'd be thicker at the edges, thinner in the middle, and thicker at the edges. That would be a diverging lens. This is a plano-convex lens. This side is convex, that side is plane. You could have flipped them the other way and done the same thing. But this is thinner on the edges, thicker in the middle. So all 3 of these are called converging lenses. All examples of converging lenses are called thicker in the middle, thinner on the edges. They have positive focal lengths. Okay? They are thickest in the middle. That's the key. Now, these two, in my mind, are a little harder to deal with. They really aren't, but this one's, to me, the easiest to deal with, the biconvex, especially if they're the same curvature. Okay? Here are some thin lenses, but these happen to be diverging lenses. This is biconcave, not convex. Concave on this side, concave on that side. Thinner at the middle, thicker at the edges. For people who are severely nearsighted, take a look at your glasses, you'll see they're thicker on the outside, thinner on the inside. Any of you really nearsighted? Okay, you don't look like you have those kind of glasses. My major professor at Nebraska, oh man, thick, and so much so he was so nearsighted that actually I think that his retina was too long, and he actually had a torn retina because it could not, the curvature was too sharp, and they did emergency surgery and tacked it back in. He could have lost vision, but his lenses were very distinctly like this. This is a convex concave. Convex on this side, concave on this side. This is what I was saying about before. A larger radius here, smaller radius here, making thicker on the outside, thinner on the inside. That's going to be a divergent lens. And this is a plano concave, and again, thicker on the outside, thinner on the inside. So those are all diverging lenses. They have negative focal lengths. Just remember that. If they're thicker in the middle, thinner on the edges, they have positive focal lengths. If they're thinner in the middle, thicker on the edges, they have negative focal lengths. These are thickest at the edges, thinnest in the middle. Okay? Now, let's talk a little bit more about the focal length of lenses. Focal length, or little f, is the image distance that corresponds to an infinite object distance. In other words, if you place, if you have parallel rays coming in, for instance, parallel rays coming in, and they focus, they bend toward a single point. That point is the focus, and that length is the focal length. Same as for mirrors. Okay? A thin lens has two focal points corresponding to parallel rays from the left or from the right. Okay? A thin lens is one in which the distance between the surface of the lens and the center of the lens is negligible. Okay? That's what they mean by thin. Surface of the lens, center of the lens. Even when they're thicker in the middle, that distance is negligible. The distance between the surface and the center. That's why they call them thin lenses. Okay? Now, we're going to try to do this in lab. The trouble is, one of my better, laser lights died. So, Wednesday, do any of you have any laser pointers? You don't? Okay. I've got some that the last time I used them, they were working. But my best one, I don't know if the battery died, or I don't know. I just can't get it working. Okay? So if you had parallel rays coming in, and this corresponds to parallel laser light, they go make a nice blue thing. And if this is a converging lens, like it is, thicker in the middle, then notice all the rays get bent toward the center. That's the focal point. Okay? And since it's a converging lens, that's called a positive focal length. Okay? Now, the parallel rays pass through the lens, converge at the focal point. The parallel rays come from the left or the right of the lens. Now, most of the time, I always have the object on the left-hand side and the rays coming from the left going to the right. You can draw it the other way, but why you make it difficult, okay? So, whichever way it is, if it's a converging lens, thicker in the middle, thinner on the edges, then the focal point, there's always two focal points, but the primary one is on the opposite side, because that's where they're converging. However, if you had light coming from the other side, then they would converge on this one. But the focal length is the same on either side. Even though this has curvature and this one doesn't, we still count the focal point as the same. Okay? Does that make sense? Okay. Now here's a diverging lens. If you had these parallel rays coming in to a diverging lens is thinner in the middle. This is harder to see, but it's thinner in the middle, thicker on the edges. So now the rays diverge as they go away. There is no focus on the right-hand side. They appear to be coming from a focal point on the left-hand side, the same direction as the incoming rays were. If that's the focal point that you're dealing with, that's a negative focal length. Parallel rays diverge after passing through the diverging lens. The focal point is the point where the rays appear to have originated, which would be over here. That would then be a negative focal length. Okay? If they converged on the opposite side, that would be a positive focal length. Okay? Now, if the rays came from the other direction, then they look like they came from the focal point there. Okay. And what hopefully you're noticing now, parallel rays always either actually go to a focal point or they look like they're coming from a focal point. Same way as they were with mirrors. Okay? So we use those same rays. So here are the lens equations. Just like we had the equations for a mirror, here are the lens equations. Okay? Now, again, they like to do P as the distance of the object. Okay? And frankly, folks, that's always positive. Okay? I like to call this DO. It just makes more sense to call it that way. Okay? Now, they're only showing 2 rays now. Later they'll show 3. Why they don't show 3 now, I don't know. Okay? But here's the first one. Parallel ray from the object, parallel to the lens axis here, the principal axis. Parallel here, bends toward the focal point on the other side. Okay? And then it keeps going through that. The second ray, which is the second easy one to do, is just go through the center of the lens and keep on coming. There's no refraction if you go through the center of the lens. Okay? Now, the focal point is the capital F. The focal length is a little f. And this happens to be positive because it's on the opposite side of the lens as the object. Okay? So that's counted as a positive focal length. Okay? What they call Q is the image distance to the image, so I call it DI. That just makes a lot more sense. I call this HO, height of the object, call this HI, the height of the image. Okay? Now, since this is a converging lens, that means the rays going through it are going to converge onto an image on the other side, especially if the object is outside the focal length. Same thing it was for a mirror. The geometric derivation of the equation is very similar to that of mirrors, and the equation looks just like 1 over dO plus 1 over dI is equal to 1 over F. Exactly like for a mirror. The only thing that's a little different here is, well, 2 things. Q is positive if it's on the opposite side of the lens as the image, as the object. The image on the opposite side, whereas in a mirror, it's positive if it's on the same side as the mirror. Well, that's where the rays are, okay? And here, the focal point, the focal length is positive if it's on the opposite side of the mirror from where the object is. And because that's where the rays are really going, okay? They can't go to the opposite side of a mirror because you can't get past the mirror. But they look like they come from there. So those are the 2 differences. P is just about always positive, okay? Q is positive if it's on the opposite side of the lens as the object. The distance of the object image is positive if it's on the opposite side of the lens from the object. And F is positive if it's on the opposite side of the lens from the object. Okay? F is focal point. The magnification equation, just like we did before. Now I call this HI over HO and minus DI over DO. I call this DO and DI. Okay. You can use the one the book uses. It just makes more sense to make it make more sense. Okay. They look just like the ones for the mirrors, It's just a definition of what's positive and what's negative. Okay? Those are called the thin lens equations. Okay. And we'll get to the signs of them. I've already said them, but let's do them again. The equations can be used for both converging and diverging lenses. The difference will be the signs. The converging lens has a positive focal length. A diverging lens has a negative focal length. Always. Okay? If you're on the front side of a lens, that's usually where your object is, the incident light, the front side of the lens. If the image is on that side, that's a virtual image. So they call it the virtual side if you're talking about image, front side if you're talking about object. If you're over here, the P is always positive, and the Q is negative if the image is on the same side as the object. Okay, now, the back side is, they call the real side. It kind of drives me nuts. If P is positive on the incident side, if this is the incident side, how can the object ever be over here? It can't, because it's incident from this side. So why they even put this in here, I don't know. But the Q is positive on this side because that's where you would be going, and that would be the real side of the lens. If you have a real image, it's going to be on the opposite side of the lens as the object. Okay? And the focal point will also be on that side. Okay? All right. So, I don't see if this is the incident side, that's where your object is. Okay? How can you ever have the object over here? Maybe you will see an example where it is, and I'll eat my words, but I just don't see how you could. If you had the object over there, make that the positive side, and the rays are going in the opposite direction. Okay? So, here's the sign convention of the table again. They've already shown it once. Okay? Thin lenses. The object location, I call it DO, distance of object. If it's in front of the lens, meaning on the side where the incident rays are, it's positive, and that's where it always is, okay? I don't see how they can ever say it's in the back of the lens, because if the object's over there, that's the front of the lens. Right? So it makes no sense. The image location, which I call the distance of image, DI, if it's the same side as the object, then it's a negative. If it's on the opposite side of the object, then it's a positive. Okay? The lens radii, and they say R1 and R2. Now, we haven't used those radii at all. Okay? But the first radius would be the first you get to. That would be, if that is in front of the mirror, that first radius, then it would be a negative radius. If it's the other side, it's a positive radius. The R2, same deal. Okay? If they're in front of the lens, the radius in front of the lens, that's a divergent lens. So those are negative. If the radii are in front, on the back side, then it would be the radius is positive. Focal length F, if it's a convergent lens, is a positive focal length. So a divergent lens is a negative focal length. Now, we'll see some examples of a converging lens having a virtual image. So they won't always be convergent. We'll see that later. So let's look at the focal length for a lens. The focal length of a lens is related to the curvature on its front and back surfaces and the index of refraction of the material. This is sort of a complicated looking equation, but this is called the lens maker's equation. Unless you're going to be a lens maker, I don't know if you really need to know it, but we'll do it. one of the focal lengths, notice that a lot of them are reciprocal equations. One of the focal length is n minus 1 times, okay, n being the index of refraction of the lens, 1 being the index of refraction of the air generally, so n minus 1 times 1 over R1, which I think is the radius of the first surface you come to, minus 1 over R2, which is the second surface you come to. Okay? Now, remember that planar mirror, planar lens, that one side is actually a plane? You remember that? What's the radius of a plane? What's the radius of a plane? Curvature, yeah, I can picture the radius of that. Somewhere out there is the center of that curve. What if that's a plane? What's the radius of that? Infinity. But then 1 over infinity is 0. So one of these is going to be 0. If one of those is a plane, then its radius is infinity, and 1 over infinity is 0. Okay. I don't know if lens makers really use those very much, but you could. If you ever run into it, that's what it is. So, what are arrays diagrams for thin lenses? Very, very, very similar to what they were for mirrors. Array diagrams are essential for understanding overall image formation. Three rays are always drawn. First ray, just like before, is drawn parallel to the first principal axis of the lens. It passes through the lens, or appears to come from, one of the focal points. Okay? So I don't like for it to say through the focal length. It should be through the focal point. Passes through or comes from one of the focal points, not lengths. Okay? So if it comes in parallel, it goes out through a focal point, or appears to come through a focal point. Okay? Second ray is drawn through the center of the lens, and it keeps going straight, continues in a straight line. The third ray is drawn from the other focal point and emerges from the lens parallel to the principal axis. So if it goes through the near focal point, then it comes out parallel. The lens comes out parallel. So the only difference is they used to call this 1, 2, and 3. Now they do it 1, 2, 3. They changed the order of these two, but it doesn't really matter. There are an infinite number of rays, but these are the convenient ones, because one's parallel, one's through the center, and one's through the focal point. So it makes them real easy to draw, relatively easy to draw. Okay? So here are some examples of these. So, the object in front of and outside the focal point. Now, if this object was inside the focal point, different things happen. But if it's outside the focal point, okay, then, and it's a converging lens, here are our three rays. The one that comes in parallel to the axis here, when it goes through the lens, it goes through the opposite focal point. Okay? Keeps on trucking. Okay? The second ray, unlike the mirror, but second ray here goes straight through the center and keeps going straight through. Doesn't refract at all. Okay? The third ray goes through the first focal point, and then it gets refracted parallel to the axis. Those all converge. They converge on the opposite side. Since they converge on the opposite side, it's a real image. And guess what that real image is? Always. Real images are always inverted, exactly. Okay? Now this one, hard to say, but it looks like the magnification is exactly -1. Minus because it's inverted, but 1 because this looks like it's about the same height as this. And frankly, if this is exactly twice the focal point from the lens, then that will be exactly the same. actually this looks, to me, looks a little further here, a little closer there, a little further here, a little closer there. So this is probably slightly reduced, don't I? Okay. Well, what happens if you place the object inside the focal point? It's a converging lens, but guess what? The rays can't converge coming out because the object's inside the focal point. Okay? So the first ray is the one that's going in parallel. When it goes through the lens, it goes through the opposite focal point. Got to. They all do. Okay? The second one goes through the center of the lens, keeps on traveling. The third one acts like it's coming from the first focal point, goes up and hits the lens, and then comes out parallel. Look at that. These three rays on the outcoming rays, diverging. They are not forming a real image at all, even though this is converging lens, because the object is inside the focal point. Okay? What is the image? Draw a dotted line back from all three of these refracted rays. There you get where the image is. Okay? Tell me three things about that image.
It's upright.
It's upright. If it's upright, what is it? It's upright. It's always. Say again.
Real.
No. If it's inverted, it's always real. If it's upright, it's always vertical. And then this one in particular, what can you tell? The image is
Inverted.
no, it isn't. It's upright. But the image is second, bigger than the object. So therefore it's magnified. Okay? A positive magnification because it's upright, and a magnification of absolute value greater than 1, meaning it's bigger. I call it magnified. Okay. Now, what do you reckon would happen if you place? See, here the object is outside the focal length, focal point. So therefore, the image is real, inverted, and depends on the size. Okay. Here it's inside the focal point, and that makes a upright, virtual, magnified image. Okay. Now, what would happen if you're right on the focal point? What would happen if you're right on the focal point? There is no image. Everything comes out parallel. There is no image at all. Now, if you do the focal point, focal length from the center of the lens to the focal point, that's the focal length, and exactly double that, that gives you what you call the center of curvature. And if you're inside the center of curvature, in between the focal length, focal point and center of curvature, then your image over here is going to be magnified, and between the mirror and the lens at the focal point. If you're, magnified, let's start that over. If the object is outside the focal point, outside the center, then the image is going to be inside the center, between the focal point and the center, and it will be reduced. If it's inside the center, between the focal point and the center, then the object's going to be outside and magnified, but inverted, of course. Okay. So you see, if you take this object and go closer and closer to the focal point, then it starts out a small image, gets bigger, 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 and bigger, and then it blows up, and it's at infinity here, and then inside it flips it back here, and it starts off enormous and then gradually goes down, but always larger than the object. Okay. Now, ray diagram for a converging lens when the distance of the object, P, I call it DO, is greater than the focal length, outside the focal length. When the object is in front of and outside the focal point of a converging lens, the image is real, inverted, and on the back side of the lens. Okay? And this is the same as what we just saw. It appears to me that's a little smaller, which would indicate to me that this is outside the center, and this would be between focal points. Image is real. If the image is real, what else is true about the image? If the image is real, what else is true about the image? Inverted always, and on the opposite side of the lens. So this is the difference between lenses and mirrors. If it's a real image, it's on the front side of the mirror, okay? If it's a real image with a lens, it's on the opposite side of the lens. Okay? They call it back side. I like to call it opposite side. Okay? Here we have a converging lens, but the distance of the object is less than the focal point. In other words, the object in between the lens and the focal point is so it's going to be diverging on that side, apparently converging over here, but always magnified. Always magnified. And if it's a virtual image, what's always true about it? Virtual image, what's always true about it? Upright, exactly. Exactly. Image is virtual, it's upright, and it's on the same side of the lens as the object. Okay? So it makes it virtual. It didn't really converge on the other side. And then for a diverging lens, we hadn't done it yet, but let's do it now. Wherever you put this object, oh, here's the object. Wherever you put the object, the three rays are again. First ray is parallel to the axis of the lens, okay? Parallel to the axis of the lens, and then, because it's a diverging lens, it's bent up as if it's coming from the near focal point, okay? The second one goes through the center of the lens, it keeps on trying. The third one goes in as if it's going to the opposite focal point, but when it gets to the lens, it comes up parallel. Well, this is diverging. You aren't going to have an image out here. Your only image is going to be if you extrapolate backward to where those three rays look like they come from. That's the virtual image. What's always true about virtual image? What's always true about a virtual image? Always true about a virtual image? It's upright. It's got to be upright. Good deal. Okay? Now, for a diverging lens, that image is always going to be smaller than the object and closer to the lens. Okay? So on the front, same side of the lens as the object, making it virtual. Okay. Final notes on thin lenses. The point of intersection of any two of the three rays can be used to locate the image. The third ray always serves as a check to make sure you're in the right ballpark. The values of what I call DO and DI, distance of object, distance of image, are positive where the light is, okay? Wherever your object is, that's where the light's coming from. It's got to be positive. If the image is on the opposite side of the lens, in other words, the light has passed through the lens, then Q is positive, or DI is positive. But if the image is actually on the same side of the lens as the object, the light went through the lens, so the light is over there, so therefore that is a negative DI. For real objects, the light originates with the object in front of the lens. So P is positive. Finally, they say it. For a real object, P is always positive because that's where the light is. Okay? If the image is on the back side of the lens, meaning on the same side as the object, no, I'm sorry, the opposite side of the object, then Q is positive. Okay? Or DI is positive. Okay. Combination of the thin lenses. The image produced by the first lens is calculated as though the second lens were not there. So this is if you have a series of lenses. What you do is deal with the first one first, don't pay any attention to the next one. Then, the light then approaches the second lens as if it had come from the image of the first lens. So you have the object, the first lens, deal with that first lens, then you have an image, wherever that image is. Wherever it is, then take that as if that's the object of the second lens and treat that. Do all the things you have for that, and that will give you a third or a second image. If there's another lens, treat that as the object of the next one. Okay? The image formed by the first lens is treated as the object of the second lens. The image formed by the second lens is the final image of the system if you have a two-lens system. Okay? You could have three or more, but we're going to stay with two. If the image formed by the first lens lies on the back side of the second lens, okay, there is where P could be negative. Okay? If it's not really the object, but is the image of the first lens, but now becomes the object of the second lens, that's when it could be. Okay, so I'll take it back. That then would be a P being negative, okay, or DO being negative. Then the image is treated as a virtual object for the second lens, which is rather bizarre. The overall magnification is the product of the magnification of the separate lenses, okay? And when you multiply the signs as well as the numbers. It is also possible to combine thin lenses and mirrors. And in fact, Isaac Newton, guess what? He did that. They had developed telescopes that were all refracting telescopes. And they had to be big and fairly bulky. Their lenses were huge, easy to break, easy to scratch, easy to have deformities in. And he used a reflecting mirror and then dealt with the light. That made it much smaller, much shorter, and more accurate. Okay? So he combined a thin lens with a mirror and came up with a much better telescope. It's called the reflecting telescope. Okay? Here's a combination of lenses. This is the example. And let's see, is this going to be one that we actually have in the book? Okay. I haven't been turning the pages as I should have. Those three that we looked at, those were figured 23, 25, bottom of page 766. Here, quick quiz, three of them. A clear plastic sandwich bag filled with water can act as a crude converging lens in air. If the bag is filled with air and placed underwater, is the effective lens converging or diverging? I would say diverging because your indices of refraction are opposite. So let's see if that's what the book says. I would say that's 23, 4B. Exactly, diverging. Okay, 23.5. In figure 2325A, there, that's it. Okay, 2325A, I'm pretty sure that's it. Yeah. The blue object arrow is replaced by one that is much taller than the lens. How many rays from the object will strike the lens? Okay. What they're meaning there is, what if you had an object that tall. Okay? Then that first ray, the parallel ray, let me make it baby blue like they did. Want it baby blue or just light blue? Blue or light blue? I don't care. Light blue, okay? Then this one would come in, that's supposed to be, goodness gracious, parallel. Then even though it doesn't even hit the lens, you still treat it as if it did, okay? You still treat it as if it did, okay? All right. And you can do them all then from there. The others will be fine. How many rays from the object will strike the lens? I don't really know what they mean here. I think they mean if the first one misses it, the other two will hit it. So, well, I thought they meant of the rays we usually talk about. An infinite number of rays always hits the lens. I mean, because they're coming from everywhere. We just pick out 3 that are convenient for us. All right. Bizarre question. 23.6. An object is placed on the left of a converging lens. Which of the following statements are true? An object is placed on the left of a converging lens. It's like either one of those objects there. Which of the following statements are true and which are false? The image is always to the right of the lens. True or false? An object is placed to the left of a converging lens. Which of the following statements are true and which are false? The image is always to the right of the lens. False, exactly. This figure here. The object is to the left of the lens. The image is to the left of it. So that's a false. B, the image can be upright or inverted. It's a converging lens. Say again? True, because it could be. That one's upright. This one was inverted. Okay? So that one's true. The image is always smaller or the same size as the object. False, because it could be larger than the object. So that was false, true, false. Got it. Okay. Now, applying physics 23.5, vision and diving masks. Okay. That's pretty interesting to read through and follow. Example 23.7, images formed by converging lenses, and we've done some like that, but you can take a look at that one. 23.8 is the case for a diverging lens. We've done some examples of that. I'll be glad to do those if you wanted to. 23.5.2 is combinations of thin lenses, which is what we were about to do. In fact, we had done the other. This is our 2 lenses in a row, and let's see if that's the same one we have here. It looks like it. Okay? 2 converging lenses are placed 20 centimeters apart. Yep, those are 20 centimeters apart, as shown in this figure. Okay? With an object 30 centimeters in front of lens 1 on the left. 30 centimeters in front of lens 1 on the left. Got it. Now, A. If lens 1 has a focal length of 10 centimeters, and that's what they showed there, focal length of 10 centimeters, locate the image formed by that lens and determine its magnification. So let's do it, to it. Okay? It first says, locate the image formed by the thin lens. Now, what does it mean to locate it? What are we looking for? What does it mean to locate it? What are we looking for? What's our variable that we're looking to find the answer to? It says locate it. That will be told to you by the of the image, right? Distance of the image. That's the location of the image, right? Now they call it Q, I call it DI. Okay? I find that's easier to deal with. Okay? So, let me get back to black here for a moment. Okay? Now, let's do it geometrically first, and then we'll do it analytically. Here's ray 1. Leaves parallel, the object 1, parallel to the axis of the lenses. Okay? When it hits lens 1, it has to go through the opposite focal length. There it goes. Okay? Then, number 2 goes through the center of the lens and keeps on trucking in a straight line. There's again I1. The third one is the one that goes through the focal point, okay, the same side focal point, hits the lens, comes out parallel to the axis. So there it is, so there's your I1. Okay? That shows you where it is, but it doesn't locate it for you. You've got to use the formulas to do that. And what is that formula? 1 over dO plus 1 over dI is equal to 1 over F. Okay? And guess what? We know dO and we know F. So we solve for dI. So here's what I would do. There's several ways you could do it. But what I would do would be subtract 1 over dO from both sides. Okay? That goes away, right? So this gives us dO minus F over F dO. Okay? I did that sort of rapidly, but you see, here's your least common denominator, the product of the two. To get the numerator here, we multiply, to get that denominator, we multiply this one by dO, so we multiply this, so that gives you a dO there. To get this denominator here, we multiply by F, and that would be minus F there. So here is that subtraction problem. Okay? Is that too much shell game, or did you see what I was really doing? Okay? Now, that gives you 1 over DI. I want to know what DI is, so I'm going to invert that and invert that. So that would be then, that would and give you that DI, distance of image, is equal to F dO over dO minus F. Okay? Well, let's plug and chug then. Your first focal length is a positive. It's on the same side of the lens as the object is. So that will be a 10. Multiplied dO, dO was 30. Okay? Divided by the difference between dO and dF. dO is 30, F is 10, that difference is 20. And again, that's centimeters. Well, these 2 centimeters multiply this one. You can wipe out one of them with that one. So this gives you 300 divided by 20. Okay, the zeros go out, that gives you 15 centimeters. So 15.0 centimeters. Positive, meaning on the same side. So that means that DI here is 15.0 centimeters. Do you see that? And that's exactly what they show. I'm sorry, I didn't realize they showed it. Okay? Good deal. Okay? Now that's 2 converted, blah, blah, blah. Okay? Lens 1 has a focal length of 1 or 10 centimeters, we did that. Locate the image, we did that. Oh, determine its magnification. What is its magnification? What is that formula? Capital M is equal to, anyone remember the magnification formula? There are two of them, in fact. Thank you. There are two magnification formula. Okay. By the way, we have just barely, no, I'm sorry. Yeah, we've been in the lab period. No, we haven't. We just got into the lab period. 5:30 to 6:20 was class, and then 6:20, okay, 6:30 to 9 is lab. So FA is still here. Tia isn't here and probably won't make it tonight. Megan's still here. Shakina just barely made it in the lab period. Charity, not here. Courtney, still here. Sam, kind of here. And Brianna didn't make it yet tonight either. Do y'all need a little break?
Yes.
Say again?
I'd be happy to stand up.
What's that?
I said I'd like to stand up.
Okay, well, let's take a little break. I can use one
Let's
too.
testify.
What's that? Yeah.
Let's testify.
Okay. So,
The lab.
what's that?
The lab.
Oh, okay, well, let me, yeah, well, I can come back to this. I think everything will still be there. Just about got the light again. All right, what we did, we got the distance of the image. That was locating the image. That was what number A said. If lens 1, blah, 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 locate the image form. That's what DI gave us, located the image. There we got it, 15 centimeters. Okay? And determine its magnification. And that's where I left off last time. What is the formula for magnification? There are actually two of them. Huh? The formula for magnification. I'm sorry?
I don't know.
Okay, well, it's the height of the image over the height of the object. Because that shows how much magnified the image is from the object, right? But we don't have either one of those, okay? So there is another one that works too. It's just the negative of distance of image over distance of object. We have both of those. And what would that be then? What would that be then?
You said the difference of both of those?
I'm sorry?
You said the difference of both of those?
The difference of both of those? Is that what you said?
Is that what you said?
No, I said it's the, okay, depending on where you're talking about, it's the quotient of the distance of the image to the distance of the object, minus the distance of image over distance of object. What would that be in this problem? Pardon me?
I don't know.
Well, we just found distance of image to be 15, so it'd be minus 15.0 centimeters. That's distance of image. What was distance of object? That was given in the problem. Right here it is, over 30.0 centimeters. And what would that be? Negative 1/2. Now what does that mean? What does the negative mean?
Backwards?
I'm sorry?
It's backwards?
It's inverted.
Inverted.
And sure enough, the image is inverted, right?
Right.
Okay. And what's the 1/2 means? Reduced in size, smaller than the object was. And sure enough, it is. So there's the magnification. So now, if we knew either the height of the object or height of the image, we could get the other, okay, because that's the same magnification. All right, now, That finishes A. We got 15 centimeters and negative 0.5. We said negative a half. Fine. To give significant digits to be negative 0.500 centimeter. Oh, magnification has no unit, sorry. Okay. Okay. Now, the B part says, if lens 2 on the right has a focal length of 20 centimeters, okay? Now, the distance from lens 1 to lens 2 was 20 centimeters, which means the focal point of the second lens is right smack dab in the middle of the lens 1, okay? So there's your first focal point. I wish they hadn't put it as red. They did for F2, but it just, okay. I would have chosen another color. But anyway, all right. Locate the final image formed and find the total magnification of the system. Locate the final image formed. Okay? Now, where do we start?
We use the same formula?
Yeah, but where do we start? I'm sorry?
I'm not sure.
Okay. The image from your first becomes the object for the second. So we start here at this image. Now, where is it compared to lens 2?
I mean, it's to the left of lens 2.
What's that?
It's to the left of lens 2.
It's to the left of lens 2, which is correct. We want it there. That's good. It could be to the right because it's just an image, but it is to the left of it, so that's fine. Where else would you say it is? How far from lens 2?
It doesn't say.
I'm sorry?
It doesn't say.
You can get it, though.
By calculating the distance.
What's that?
By calculating the distance.
Okay, do so. He decided to come back. Okay, good. All right. I know, I'm just kidding. Okay, the question is, we're continuing in the two lens system here, and we determined that the image from the first lens becomes the object of the second lens. And we were trying to determine where that is. And FA said it was to the left of lens 2. Sure enough, it is. How far to the left of lens 2? Well, it's pretty easy to calculate, isn't it? We see here that the two lenses are 20 centimeters apart, and this one's 15 centimeters from this one. So what would that put it here? Say again? 5, exactly. It's 5 centimeters in front of lens 2. So, you want to do this in a different color? What color would you like to use? What color would you like to use?
Green.
Green. Okay. Light or dark?
Dark.
Okay. I agree. Dark, I think, will be better. Okay. So now we're calling this distance of object now, even though it's the image from lens 1, but it's the object of lens 2. So I might put a 2 here, meaning lens 2. Okay. So let's use our same 3 rays that you normally would use. Okay. Now the numbers change, but it's okay. Well, the colors change too. Here is a ray that goes parallel to lens 2. You see it? Goes parallel to lens 2. Where does it have to go? I mean, parallel to the axis into lens 2. Where does it have to be bent toward? Any ray coming in parallel to the axis, where does it get bent toward? Any of the rays coming in parallel to the axis, where does it get bent toward?
I don't know.
Well, can you see it? The ray coming in parallel to the axis here hits the lens. Where does it get bent toward? The focal point of that lens. Always. If it comes in parallel, it goes out, it goes toward the focal point. Okay, so that one goes that way. The second one is the one that leaves this and goes to the center of the lens. Where does a ray that goes to the center of the lens do? What does it do? It what? What were you going to say? Huh? Yeah, well, I was pointing to it. There's a ray that goes through the center of the lens. Where does it go? No, it doesn't go through the focal point. It goes straight through the lens with not being diffracted. If it goes to the center of the lens, it's not diffracted. So it goes straight through. That's why it's a straight line right there. You see it? Okay? And what's the third ray? Unfortunately, this coincides with another one. The third ray is the one that looks like it's coming from the focal point on this side. Okay? Boy, they don't draw this one well at all, do they? No, they don't. Well, it's the one that looks like it's coming from the focal point on this side. It keeps going through here, okay, and it comes out parallel, okay. Now, they didn't draw this one well, okay. It comes out parallel. Something coming from a focal point goes through here, and when it hits the lens, it comes out parallel, okay. Now, what you have to do here is extend this backward, and sure enough, it reaches that same point. It reaches the same point as this one extended backward, this one extended backward, and this one extended backward. Okay? So sure enough, there's the image 2. From the image 1 being the object of the first lens, it becomes the image. The image of the first lens becomes the object of the second lens. Okay? So, let's use our formula. Okay, we were doing green, so let's continue to use green. What was that formula again? The lens formula, thin lens formula. Same as we used before.
Was it the N is?
Not yet. That's the magnification. We're going to do that, but we got to get the distances first.
I don't know.
It's this one right down here. 1 over dO2, now I'll say, plus what?
1 over
dI2, so we'll know we're talking about this, is equal to 1 over F2. Okay? Now they already told us that F2 was 20 centimeters. This is now F2, because you see that's from here to there is 20 centimeters. We already know that DO2, was 5. That's what Sam just told us. 5.0. Probably they put 00. I don't think it makes a lot of sense to centimeters. Okay? So we want to calculate DI2. Similar to what we just did, right? How do we get that? We're looking for DI2. We know DO2, we know F2. How do we get DI2? Either one of you. Say again? For what? I'm sorry? For DI2. So first I want to solve for 1 over DI2, because that's a term here. So let's subtract 1 over DO2 from both sides. Okay, so those disappear. So 1 over DI2 is equal to that difference. Well, let's figure out what that difference is. Again, least common denominator is F2 times DO2, exactly. Okay, what's the numerator? First numerator would be, if that's your common denominator, this one had F2, what do you have to multiply this by to get that? How do you get from here to there? What do you have to multiply by?
Can't see where your cursor is.
Okay. Here's this denominator, there's your common denominator. What do you have to multiply this by to make it that? DO2. So if you multiply the denominator by DO2, you must multiply the numerator as well, so that becomes a DO2 for the first one. All right, that's not D-oxygen, by the way, okay? What do you have to multiply the second denominator by to get this one? F2. So minus F2. Okay? Minus F2. Okay? Now, that gives you 1 over DI2. So to get DI2, we invert, right? So let's do it over here. DI2 then is equal to F2 DO2, I forgot to put the 2 in, divided by DO2 minus F2. So let's plug in what we know. What is your F2? 20. That would be 20.0 centimeters times, what's DO2? 5 divided by the difference of DO2 minus DF2. This minus that would be what's DO2 minus minus F2? DO2 minus F2. What sign? Huh? Minus? Is that what you said? No, it's 15. It's DO2 minus F2. There's F2. This is DO2. DO2 minus this would be what sign? Huh? It's 15, but what sign? 5 minus 20. Negative sign. That's important. Very important here. So that would be a minus 15.0 centimeters. Okay? So our numerator here is 5 times 20 would be 100 cm divided by a negative 15 cm, 0.0 if you wanted to. With a calculator, can you figure out what that is? You can actually divide numerator and denominator by 5 if you wanted to. That would be a 20 over 3, negative. Well, 3 will go into 20 how many times? How much? Really? More like 6?
6.
Okay.
5.
6.
6.
6.67. I'm going to round it. Okay. Centimeters. Because this is centimeters squared. This is centimeters, so that wipes one of them out. So that gives you, only it's a negative. Now what does that tell you if the distance is negative? Distance of the image is negative. No, the height is negative. Distance negative means it's on the front side of the lens, on the same side of the object. If it's on this side, that would be a positive distance of the object. Negative puts it over here. And this one was 5 here. They never showed it. We showed it. 5 here. Right up there we showed it. Okay, and this is 6.67. So there it is. And it's a negative also over here. Okay, so there is your second image. Okay, so we found the location of it. Now what do we do for the magnification? And again, we don't know height, so that first formula doesn't tell us anything. The second one, though, is minus di over do, right? Now this is all 2's now, not the first one, okay? And what is minus? Okay, well, I'll put the minus sign. di2, that's what we just found. That's this. That was di2, right here, was minus 6.67. So minus a negative 6.67 centimeters divided by do2, and that distance was 5.0, however many zeros you want, centimeters. So the centimeters go out, and that's going to be something of the order. Do you have a calculator? Okay. Say that one more time. 1.33. Let's just leave it 1.33. And that is a minus, so that's a positive. Okay. And it's a dimensionless quantity. Now, here's the thing that's a little bizarre here. This was a negative magnification here. And this is a positive magnification from here to here, meaning if this was inverted, that's inverted. That's what a positive means here. Most of the time, a positive magnification means it's upright, but it really means it's the same as the object. This object was negative, so this one's going to be negative too. So, but the question they asked for, they did ask for what is the, if lens 2 on the right has a focal length of 20 centimeters, locate the final image. We did that. That's di2, okay? But it says, and find the total magnification of the system. So what's the total magnification of the system? It's the product of these two magnifications. So it's negative 5.5 times a positive 1.33. What does that mean? 0.6777?
6.65.
Again?
Negative 6.65.
Okay. The total magnification, I'm going to put M maybe I should do a different one. It's the product of those two, and you said like negative 0.665. Is that what you said? I'm just going to round that to 6.7. Okay, and that will be the magnification. They put 665 also. Really, because of round-off errors, I think it really is 6.7. Okay, and sure enough, from the beginning to this one, it's a larger magnification than this was, but still not huge. Okay. Now, I reduced down to only 2 significant digits, mostly because when you subtract and came up with a 5, I don't think it's legal to do 5.00. I think it's still 5, so that's why I rounded that way. I'm not going to argue with them. They can round to 6.65 if you want, 0.665 if you wanted to. But I think we're a little better off just making that 0.67. But you see the general idea. Okay, so that was your combination of thin lenses. The key is have the image of the first become the object of the second. Take it all the way through. Ignore that second lens to begin with. Take it all the way through the first, and then treat that image of the first as the object of the second, and go on from there using your ray diagrams and your formulas. Okay. Okay. There's also example 23.10, which is thin lenses and a concave mirror. Okay. If you want to see that, I'll be glad to do it for you. Do you want to see it? Huh? Okay. Then we move on to lenses and mirror aberrations. Okay. It's 23.7 on the slide set, but it's 23.6 in our text. Okay. Now, one of the basic problems of systems containing mirrors and lenses is the imperfect quality of the images, largely the result of defects in shapes and form. It's really hard to form perfect lenses and perfect mirrors, so you're always going to have a little bit of a problem there. I think they've gotten much better at glasses now than they used to. We live in a 1930s house. Actually, it started in 29, finished in 30. And you can tell the original panes and those that have been replaced, because the original panes have some weightiness to them, because the glass isn't perfectly flat, or the index of refraction isn't the same throughout. So you do get some imperfect quality of the transmission. Of course, I think in an old house that gives it character. If you're trying to do images, that gives you problems. Okay, no character. 2 common types of aberrations exist. One is called the spherical aberration, and the second is called the chromatic aberration. The spherical aberration has to do with thicknesses of lenses and things like this, and they don't quite match up to what our assumptions are. The chromatic aberration is the fact that anytime you go into a different medium, you start getting the spreading of light, right? The prism effect. That's what the chromatic aberration is. So let's take a look at this first, the spherical aberration. Result from the focal points of light rays far from the principal axis are different from the focal points of the light rays passing near the axis. Okay? So these rays that are near the axis, okay, basically converge right there. Those farther from the axis converge right here. And that gives you an aberration. Refracted rays intersect at different points on the principal axis and give you not a clear focus, but a fuzzy focus. Okay, basically. Lack of a better term for it. For a mirror, the parabolic shapes can be used to correct for spherical aberration. Because a spherically shaped mirror, even though we use radius and we use the focal point as half the radius,
really it's far better to use a parabola because those really do focus very nicely, okay? Do you remember when they put up the Hubble Space Telescope? You probably don't. You're probably too young to think anything about it. I don't know where the error came, but someone had miscalculated or done something wrong because the early images we got off of that were awfully fuzzy. And they had to go back up, astronauts doing spacewalks, and actually reshape the surface. I don't know if they put more stuff on it or ground down what was there. I don't know what they did, but it was quite, but since then, it's been beautiful images. And I don't know which of these it was or if they just made an error somewhere. I do not know. But I do know that the images were fuzzy, which to me would have been sort of the spherical aberration problem. And they probably had to ground them down and make them into more of a parabolic rather than spherical reflector. Okay? I don't know that for sure, but that's just a guess. Okay? The chromatic aberration is the fact that different wavelengths of light are diffracted by a lens focused at different points. Violet rays are refracted more than red rays, so the violet rays will come in. Now this is a gross exaggeration, but they come in real at a closer focus than the red rays will. Okay? Now that's from close even, but if it's very, so that will also give you a fuzziness, okay? And you'll get sort of a light shift there. The chromatic aberration can be minimized by the use of combination of converging and diverging lenses because, see, a converging lens will bring it in quite closer. If you put a small diverging on the outside, that brings them back closer together again. So that's how they take care of that combination of converging and diverging lenses. The rays from different wavelengths focus at different points. Okay? And of course, the greens and the blues and everything in between are in between these two. But if you have a small diverging lens here, that forces them closer together again. Okay. So both of these can be fixed to some extent. That is the end of this show. Okay? Like I say at the end of every chapter, there is a summary here, and maybe I don't say this enough. Don't rely on the summary. Read the text. There's a lot more in the text than they show here. And we take a while to do a chapter, so use that time in between to be reading the chapter so you can understand better what it's saying. But in the summary, they give some of the key terms, real image, like 23.1, flat mirrors, real image, virtual image, what they mean by that. 23, and they give an illustration there that's a pretty good one. 23.2, images formed by spherical mirrors, magnification, image height, object height. They give their symbols for it. I give the ones I like to use. The object distance, image distance, they do P and Q. I like to use DO and DI. It doesn't really matter. And then the focal length is R over 2, half the radius. So when you had before 2 over R, that would be 1 over F. Okay? They give some good diagrams there too. 23.3, images formed by refraction. They give some of the basic formulas you got, but they then the thin lenses, those are the more specific formulas. So they have those, and then the lens and mirror aberrations. They have the definitions plus some illustrations of that.
So what do you think is in a black hole?
What do I think is there? It sounds like everything that it can suck up. It sucks up matter, it sucks up light, it sucks up energy, it sucks up everything. So what comes out, what does that result in? I'm not sure. Except a very, very dense, high gravity system that just keeps getting bigger and fatter. Now, it seems like if it went on forever, it'd suck everything up. There are a lot of theories about what's happening that may be
On the other side of the black hole, there's stuff coming out of it in a parallel universe. I can't understand that. Okay, but there are all sorts of theories. I can't say what to say, except that it's very dense, high gravity, and just sucks everything into it.
So did you hear that we teleported photons to a satellite?
We teleported them to a satellite. How do you mean doing that?
Quantum entanglement.
Okay. I'm not sure I understand what I know what quantum means, but quantum entanglement, I've never used that. I heard that term before. Now, when you say that,
It isn't in the general teleportation definition.
right, and I was going to say that it has to be something a little beyond, more refined than that would be.
Yeah.
But interesting. I know I've heard some pretty interesting things about, what do they call them, light ladders or something like that, where things sort of climb and go. That sounds almost too good to be true, but because it's photons, they don't really, they're not affected by gravity, so it's easy for them to just move on out. I don't know. So when you said teleporting, I was thinking something like that. I don't know if that's a good rendition of what you were meaning or not, but yeah.
Let me tell you what it said. Okay, Einstein called it spooky action at a distance.
Say that one more time.
Spooky action at a
Spooky?
distance. That's what Einstein called it.
Okay, spooky action at a distance. Okay.
It says when two quantum objects
Right,
share a wave function,
right.
they come into existence at the exact same time and place. They share the same identity, even when separated. What happens to one happens to the other, wherever it exists.
Right. So how do they separate them in the first place? If they start at the same place and they're identical, how do they separate them? I don't know. Going through a lens? I don't know. Interesting. It sounds, no wonder he called it spooky. Then there's a bunch of conceptual questions, and these set of conceptual questions have more figures in them than I've ever seen in a conceptual question set, okay? So I would definitely look at some of those, especially the odds 1 through 15, because you do, those have answers in the back. Then the problems. The problems are going to be more like your test questions, and the test questions are, the problems that have answers in the book, the odds for 23.1, 1 through 19, 1 through 5, and then 23.2 is 7 through 19, 23.3 or 21 through 27, there aren't any for 23.4. Thin lenses have some 29 through 45, and the aberrations and stuff like that, they don't have any. Then the additional problems that combine several of these together would be 47, odds 47 through 65. Okay, now, yuck. I did give you the test from the previous chapter, reflection and refraction, right? I don't have this one completely made up yet, so I wish I had that.
I didn't get that one.
Okay.
This is 4 and 5.
Put them right under there. Pull up that little flap. Pull up the little flap and put them under there. Yeah, right there.
So this is, it doesn't matter. Just put them in here.
I'll put them in order. Okay. Now the last one I passed out.
Is that last class? I wasn't here last class.
Okay. We didn't have a lab for that chapter because we there. This is scary. Okay. Electromagnetism. That followed test 6. Okay. I wonder. There's test 6. 6.
People have already turned in test 6?
I don't know. Here's, oh, I was looking at the wrong one, sorry. I didn't go far enough. All right, wait a minute. Okay. There's the answer key.
Oh, let me see that one.
No, that's all right. What I don't see here is my no. I see, like I said, my answer key, but I don't see I wonder, I think I turned it in to be copied and I haven't gotten it back yet. And I went by there this morning. It may be that she hadn't gotten it done this morning and has gotten it done this afternoon. So I must not have given them out because I sure don't see them in here. So let me, unless they're right at the very end, I don't see it. All right, let me go see if I can find those, if she did them and put them in my box. I'm going to put this on. All right, so I passed out the test on topic 23, which was mirrors and lenses. We're not going to do 24, wave optics. Good chapter. It's a little more involved, less perhaps, how would you say, intuitive and geometric, and a lot more, a little bit deeper stuff, okay? But we just don't have time for it. Well, I don't think we do. The next chapter that we do is, oh yeah, and we don't do optical instruments either. That's topic 25, which is a really interesting topic too. I'd love to go on and do that one, but it's I don't think we are going to have time for it. So skipping 24 and 25, we now get to topic 26, which is relativity. Okay? And, let's see, we've got about 30 minutes left, so let's get what we can done here. Why did that go all the way back there? I don't know. This thing is rather bizarre. Okay. Sorry, we're having to wait for this to load again. So, 26 relativity. Now, once we get this one done, let me just go back one. Just take a look here. We could either go back and do quantum, once we do relativity, then hit a little bit of quantum physics. Or what I think would probably be better is go back to 20, induced voltages and inductance. I think that's a little more appropriate for this course. This is getting into nuclear physics, higher level stuff like this. I think one chapter here will be fine. I've already got labs and tests made up for this. For this, I don't have for this. So I think we're just going to do the one here. And if we have time at the end, then we'll go back and do chapter 20. That's a good topic, but I just didn't have. I was afraid we wouldn't have time to do 22, 23, and 26. So let's go on and get started on 26. Relativity. PowerPoint lectures. And one of these days PowerPoint will open. Okay, we are finally there. Start the slideshow from current slide. And we'll talk about topic 26, which is relativity. Now, there's been television shows and other things about this, but don't get confused the everyday term with what we're talking here. Here's the basic problem. Isaac Newton, of course, did his 3 laws of motion. He did his mechanics. Newtonian mechanics were very successful in describing motion of objects moving at much less than the speed of light. I mean, way less than the speed of light. However, when you get up to particle and particle particles having speeds that even get close to the speed of light, Newtonian mechanics fall apart. Okay? Don't do very well. The speed of every particle in the universe always remains less than the speed of light.
No.
No. Why not?
What about black holes?
Okay? That's sucking stuff in, so therefore the speed actually goes negative. Okay, so that's a lot less than the speed of light. So, but that's sort of the basis for all of Einstein and everybody else, is that you cannot exceed the speed of light. Okay? Now, science fiction, warp speed, yeah, that's what that's all about. Because, frankly, if you're trying to travel to a next galaxy, you would have to take enough people to populate several generations to get there. Even if you travel at the speed of light. They're that far away. So,
Not the closest one.
how far is it?
Couple light years.
I think it's more than a couple. It's more than a couple light years across the Milky Way. I mean, you're talking astronomical distance.
Let's look it up.
Okay. Altitude, let's start. Goodness gracious. The next galaxy is, goodness, they wrote it. There was Andromeda.
Holy crap.
Yes, exactly.
2.2 million light years.
Yes, exactly. Longer than we've been around. Okay. Now, how about the next closest possible inhabited planet, and star that could have an habitable planet? That's probably still many light years away. So how do you haul enough food and water, and you have to recycle a lot of stuff, and I don't know.
It's not possible.
No.
Ever.
Okay. So, all of science fiction, when they're traveling to galaxies far, far away, Star Trek, those other things, that's the fiction of science. Not science, okay.
But the Andromeda galaxy is coming toward us.
Yes. Which seems weird too, because the whole Hubble effect is that everything's supposed to be moving away at an accelerating thing. Why are they coming toward us? Because supposedly the universe is expanding, not contracting. Why are they coming toward us?
That's just a theory.
What?
That it's expanding.
Well, the Hubble redshift and everything else indicates it is. Now, maybe within a galactic group, you can have stuff coming closer. I don't know. It's kind of bizarre. Now, I've also heard that even if they are coming closer, and we were to, in some ways, intersect, there's enough distance between the stars in any of them, there would be a real good likelihood that we would pass right through each other without even bothering one another. Well, I can sort of see that for stars, because stars are awfully far apart. There's plenty of room for other stars to get through, solar systems and things like that. But what about the black holes? They're at the center. How are they going to pass through each other? I don't see that at all. So maybe the black holes don't even come close, but you would think, mystified by that possibility. All right, questions? All right. This universal speed limit that nothing can exceed the speed of light. Okay? If that is indeed true, has some consequences. The usual concepts of force, momentum, and energy no longer apply. Okay? When you get up to that kind of speeds and stuff. How can you have, say, two objects traveling near the speed of light with similar momentum, and one hits the other and gives the other? It can't give an increase if it's already near the speed of light. You can't do that. How in the world do those interact? Because you see, I can take a large ball and roll it toward a small ball and collide with it. The small ball takes off at a faster speed than the large ball. Large ball loses some speed, conservation of momentum, but this one picks it up because it's a lower mass. Its speed is increased significantly. Can't do that if they're both near the speed of light, and this is a low mass and a high mass, whatever. It can't exceed the speed of light. So conservation of momentum can't happen when you're near the speed of light because you can't exceed it. So that's just probably a really lousy example, but this is the one that comes to mind. Observers moving at different speeds will measure different time intervals and displacements, that's physical displacement, between the same two events. Okay? Well, have you ever ridden a train? Okay. Have you ever been near the station and another train's leaving, you're coming in, but you really can't tell if you're moving slowly and the tracks are smooth enough? You can't tell if you're stopped and he's going real fast, or you're going fairly fast and he stopped, or you're both going some speed and not. You just can't tell.
It happens when I'm in the car sometimes.
Yeah, and that happens in a car too. You pass somebody and you seem like you're at the same speed, but you're both going close to 70 miles an hour. So Yeah, and yeah, that same kind of stuff that do that. Observers moving at different speed will measure different time intervals. Now, here on Earth, in low speeds and stuff, the time intervals are okay. It's when you get near the speed of light, they really go whack up. Really go whack up. And the displacements go whack up too, between the same two events. And we'll see that more as we go into the chapter. The first section is called 26.1, Galilean Relativity. In other words, go back to Galileo. Why they chose Galilean rather than Newtonian, I don't know. But choose a frame of reference, okay? Us sitting in the room right now. It's necessary to describe a physical event. According to Galilean relativity, the laws of mechanics are the same in all the inertial frames of reference. What is an inertial frame of reference? It's one in which Newton's laws are valid. Why are we jumping back and forth? But anyway, objects subjected to no forces will move in straight lines. Okay, Newton's first law, right? Nothing that force should move in a straight line. Okay. Now, so as long as nothing's approaching the speed of light, all these things are true. Okay. But once you get something moving close to the speed of light, then your relative motion can go kind of haywire. Okay, we'll get to that a little bit later.
So I got a question.
Yeah.
If you're moving close to the speed of light, that means time is going slower for you.
Yeah. Right. And we'll get to that. That's exactly what we're going. But here's the other thing. Your mass is increasing toward infinity. The closer you get to the speed of light, the more massive you feel like you are, or an object is. That's why basically only waves can go near the speed of light. Even an electron cannot approach the speed of light. It goes to infinite mass. Huh?
What does that mean?
I know. We'll get to it.
Does that mean it explodes?
No, it just means it can't go there. It can't get close to the speed of light because it's massive.
What if it tries to go there?
You get slapped back. No, I don't know. Yeah. Let's see if we can go. So here's an example. Okay, Galilean relativity. A passenger in a moving truck throws a ball straight up. Okay? It appears to move in a vertical path from where he is. That is the same motion as when the ball is thrown while at rest on Earth. It appears to go straight up and straight down. But if the truck was moving, when he first threw it up, it was probably here, and it went up and came down here. But for him, he threw it straight up and it slipped right in front back down because he's moving with the same velocity the ball is. But in reality, if you were standing back here on Earth, watching when he threw it up, it was over here, and then when it was on its way back down, it was over there, and he catches it when he maybe right here. But for him, it looks like he went straight up and came down. But because the truck's moving, the ball has to be moving in that direction too, right? If the truck is moving, he's moving with the truck.
I get what you're saying.
Yeah.
But
And the ball's moving with the truck.
But okay, if I was on the back of a truck,
Right.
and I threw it up in the air,
Right.
and the truck was moving, then it wouldn't move with the truck. It would just fall down. Now, if I only threw it a small height, then yeah, it would come back down to me. But if I threw it way up in the air, then the truck's just going to go, and the ball's going to fall down where I threw it.
Okay. Okay. I think what you're describing is when it also has air resistance. The truck will,
Oh, so you're not talking about air resistance.
no, not talking about air resistance. Okay. If there was no air resistance, because when he
Question.
thank you.
Question.
You have such nice pipes. Okay.
you see when it leaves his hand, the ball also has the velocity, just like he has the velocity. So it's like this, and as long as there's nothing impeding that, as in air resistance, then it does go up and come down, because in reality it is going that way. Now, if the truck was accelerating forward, it does wind up there. Or accelerating this way, it winds up here. Yeah, and that's what they mean by an inertial system, that everything is moving with the same velocity, not accelerating one to another. So a passenger in a moving truck throws the ball straight up. It appears to move in a vertical path. Same motions when the ball is thrown while at rest on Earth. Law of gravity and equations of motion under uniform acceleration are obeyed because it's a constant velocity. That's what uniform acceleration is. This really should have been part of 201, not 202, okay, but they put it here in 202. The observer in the moving truck sees the ball travel in the vertical path when it's thrown upward. It's kind of like, and this is really a really dumb example, but I'm sure you've had your windows open at some time and gotten a fly in the car, right? You're traveling 70 miles per hour down the road, but the fly is not traveling 70 miles. It is, because it's inside the vehicle, but it doesn't sense it is flying, just like it would if it was in the room here and we're not traveling. Or are we at rest here?
In the car?
No, here in the room.
Well, no.
Huh?
No.
Why not?
Because the Earth is moving.
The Earth is moving big time. It's going around the sun. It's spinning while it's going around the sun. The sun is moving around the center of the Milky Way. There's just all kinds of motions going on. But as long as they're inertial motions, in other words, no acceleration, just a constant velocity or pretty close to it, there's no sense that we're spinning and flying through space or anything else. Of course, scale has something to do with it too. But we are really moving, I mean, enormously fast. Okay? Now, this is what I was describing before. The person standing on the ground looking at that person who really felt like he's throwing it straight up, he is throwing it straight up, but he's moving along here as the ball's moving along here, and then he catches it here. To him, it looked like straight up and down. To this person, it did this because the truck was moving. Now, he didn't sense any motion of the truck necessarily. I mean, it could be both, but it was a perfectly slick, smooth road, no noise or anything else, and no wind. In other words, the wind's going the same speed he is. He doesn't even sense he's moving anyway. She does though, because she can see he was here and he wound up there. There's a stationary observer on the ground, views the path of the ball thrown to be a parabola. The ball has velocity to the right equal to the velocity of the truck, equal to the velocity of the man. Everything has that. So the Earth-based observer sees the ball path as a parabola, whereas the guy sees he throwing it up and comes right back down to it. Now, my older brother had 2 daughters. That was it. My younger brother had 2 daughters. And finally, the first son was born into the family. Well, he couldn't get any of the girls to play with him any time. His dad was so busy, he didn't have to. So Daniel would go out in the yard and throw the football up in the air and run under it and catch it. You know, he threw and caught to himself, so he had to really perfect that art of how to do it, you know, to get that to work. So he should be teaching this because he's really experienced. I never did. I had an older brother and a younger brother. We always had plenty of people to throw balls to. Poor Daniel didn't. Okay? Beside the point. Okay. The 2 observers disagree on the shape of the path. The guy in the truck thinks it goes up and down. The gal on the earth sees that it is really going in a parabolic shape.
both agree that the motion obeys the law of gravity and Newton's laws of motion. They both do. It's just that the guy doesn't sense that he has a horizontal velocity because he's not accelerating. As long as you're not accelerating, you don't sense that you have that motion, okay? Whereas she, since she is stationary, she does see his velocity. Even though it's not an acceleration, she sees the path to do that then, okay? Both agree the laws of motion obeys the law of gravity and Newton's law of motion. Both agree on how long the ball was in the air. If they both had stopwatches, no problem there. Conclusion, there is no preferred frame of reference for describing the laws of mechanics. Seems like a pretty broad conclusion for just that little problem, but indeed there isn't. Everything follows Newtonian mechanics. Okay? Now, there are limitations. Galilean relativity does not apply to experiments in electricity, magnetism, optics, and other areas. Why? Because magnetism, well, the fields, these are all fields. Electrical fields, magnetic field, light is electromagnetic radiation. All these things, they do travel at the speed of light. So you can't use Galilean relativity with them. Results do not agree with experiments. Boo hiss. The observers should measure the speed of a pulse as V plus C. Now,
What about sound?
Sound is slower. That's so slow it probably fits. But
So
these things,
slow? You said so slow?
Yeah, but not, except for, did you hear what her paper topic was?
Doppler effect.
Doppler effect. So sound really doesn't, I guess, because the frequencies get pushed together. If they're going this way, they get spread apart if it's heading in the opposite direction. So yeah, sound probably wouldn't. At first I said it would, but it really doesn't. Now, if the observer, depending on which observer you're talking about, if in a boxcar moving with a velocity in that direction, a reasonable velocity in that direction, shine the flashlight because he's moving and so is the boxcar, would that mean that that light is moving at C plus V then? Now, if it did, you'd be exceeding the speed of light. And it can. So all she sees is the speed of light. That's all he sees is the speed of light.
What if it could?
Close. Huh?
What if it could?
Okay. That would be interesting, but actually, when you measure it, no matter what you try to do, it never exceeds that speed. Never.
How do you measure the speed of light?
They have one of the earliest experiments to do so was pretty interesting. They had a rotating, it's kind of like a gear, okay? It had teeth and spaces between the teeth, okay? Going at a really fast rate of speed, okay? And they would shine a light through that, and it would go and hit a mirror, plane mirror, and come back. And they knew the distance here, the rate of speed there, and then they had another screen back here, and for it to go through this tooth, hit the mirror, and come back and hit the next gap between teeth, then it would pulse here. Otherwise, it would be wiped out because it would go here, hit the mirror, come back, and hit on the edge of the tooth, not the space between teeth. Is that making any sense? And by varying the speeds of that, knowing exactly the distance, twice that goes up, the speeds they got, the ratio at which they would see things here, and then they back that up to the least minimum. that would be the speed of light. I think that was dizzy experiment or something like that. Pretty incredible thing. And if you did that here, or you did it without the boxcar being there, you get the same result. The speed of light would still be the speed of light. You wouldn't get a change there. So what you observed Newtonian or Galilean doesn't work if you get anywhere close to the speed of light. You actually still measure only C. Only C. Never can get it to measure anything more than C. Okay? Now,
It's almost 9.
almost 9. Let me see. I think maybe we ought to stop there. I was going to see how many more slides we did before we got to 26.2.1, but we're not going to make it because the next several are all dealing with the luminiferous effect, ether. Okay, is said a lot better than that. There's the Michelson-Morley experiment. I don't think I can get through 3 slides in the time we got left. So we will pick up and go there. Just the time that it took me to figure that out, I probably could have gotten it done, but now that that time has passed, I can't. So we'll pick up with a luminiferous effect. Ether, not effect, ether. Okay. And again, I've not taught from this book, so this has a little bit different organization than anything I've used before. So the last time I taught this was from a different text. And the time before, when I taught from this text, we never got this far. So interesting. All right.